各队的名牌包拿下来放在家，那个就放在名牌。好，没关系。
开始这些字，
到底是谁？那谁可以进来啊？还是大部分都在隔壁？
都可以进来，然后出来都可以进来。
不要走前面，走后面，旁边这样过来。
对啊，我觉得这一排比较难做。
到时候应该只有这一排会针对这个对应该。
这一排就比较难做，人家过路。
我从中间吧。
会挡到镜头。
明年要办要到对面。
明年改对面，在这边。
在菜场。然后这边场地应该至少到10个，但是有没有那么多学生不知道。已经250，他们现在已经实现200。来录在直播中，可以这边刚好在录制。
后面我说一个贴满双，之后这个
因为我看过就可以了。应该都是可以。
好书分享。
对，我的就算是有错好书分享，这样子
我这个帮我，这历史，大陆高考的历史，选修一，不能历史。
我在毕业的时候，我报过作背，所以我就给高中背报了2次，然后因为那时候是我们可以讲，因为有3题都是超大我非常的。
我要多好，没有。
真的有的时候我在睡觉的，就有人打给我。
这你们知道这么多出来当骗子？
不是我那时候真的，我也觉得
来看话就讲一个。
Okay, good morning, ladies and gentlemen. I think the time is already past 8:30, so it's a good time to start the final physics 5 of TYPT 2024. Okay, before we start to introduce the team and the juror members, I would like to make some announcement. First, this whole room is not expect you to eat or drink. Okay, so please do not eat or drink inside in this whole room. And second, after we start the physics fight, the front door will be closed. If you need to go out of the whole room, please use the door behind this room, behind you, at your back right hand side. Okay, and so I would like to introduce 3 teams. I think from the reviewer, can you from the reporter, can you introduce your team?
He is Lin Kai-zhe, and she is Wu Fangjie. He is Chen Tai-hong, and she is Chen Jie-hen. Thank you.
And then I think, opponent, you can use your microphone.
Okay, so we are from Team Cyber from Kaohsiung Senior High School. I'm Xu Hanyu, 白景仁、林玉佑、胡维忠、陈柏伟。Thanks.
Last one is the reviewer relativity.
Yeah. Okay, so I'm the captain from Team Relativity, and we're from Kaohsiung Senior High School, and my name is Lin Yongzhang. And as for my members, here is Zheng Liyang, Wang Ruichen, Luo Dazhao, and Chen Boyu.
Okay, thank you. And following, I would like to introduce the juror members. First one is the Professor Gao Xianzong. Gao Xianzong, professor from Taiwan Normal University. And second is the Professor Cai Shangfang. And third is the Professor Fu Zuyi. And Professor Chen Zhengyin. And Dr. Li Bohan. And Professor Hong Zhenyong. And following is Professor Peng Mingguang. Dr. Du Qiyou, Professor Lin Wenqing, Professor Ye Wangqi, Professor Chen Hongyi. Okay, myself is Xu Yongyuan. I will be the chairman of this thesis fight. I will not give score and try to keep the entire program running smoothly. And during this fight, I would like to notice everybody, please turn your cell phone into flight mode, or at least turn your sound off, so that no sound will interrupt the presenter on the stage. And today's thesis fight, all the problems were pre-selected. So the first thesis fight, the reporter will be Excel-Fire, and the opponent will be Excalibur, and the reviewer will be the relativity. And problem to be presented will be number 2. Droplet microscope. And we will start from the preparation time for reporter for 5 minutes. And please start the clock. Thank you. During the preparation time, please all 3 teams write down the presenter's name on the board. Okay, the time is almost up, so please start your presentation. You have 12 minutes.
Honorable juries, fellow competitors, I'm a reporter from Team Excelsior, and today I'm going to talk about topic droplet microscope. Problem statement. By looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system, investigate the magnification and the resolution of such a lens. And we will mainly focus on how is the object magnified by the water droplet, and what changed the optical characteristic within different parameters, and how is the magnification related to the resolution. And for our outline, I'll first talk about a preliminary experiment. We have demonstrated the phenomenon, and I will show the qualitative explanation. And for the theoretical explanations, we'll talk about our theory, which is the Snell's law, and we'll show the simulation of the spherical aberration. And I'll talk about our definition of the resolution and how we calculate it. And for the experiment analysis, we have 4 parameters, which is the object distance, curvature radius of droplet, thickness of droplet, and order of concentric circles. And the last one is the conclusion. Preliminary experiments. And for the phenomenal demonstration, when you drop a droplet on an object and the magnification was observed, and when the distance increased, the magnification ratio will also increase. And for the qualitative explanation, when the object distance is smaller than the focal length, the object will be an erected magnified virtual image. And when the object distance is between focal length and twice of the focal length, the object will be an inverted magnified real image. And when the object distance is farther than the twice of the focal length, the object will be inverted the magnified real image. And for the theoretical explanation, and for the modeling of droplet and magnification, we consider droplet as an ellipsoid, so that we can make the equation below here. And we model the magnification ratio as h prime over h. And for theory, we use the Snell's law, and for the theories of Snell's law, we can calculate the reflection of the light. And after conducting the experiment, we found out that the A is close to B, so that we can assume droplet as a part of a sphere. And after we assume the droplet as a part of a circle, the A will equals B and equals R, so that we can add droplet height into the consideration, so that we can get the focal length, so that we can make the equation of the focal length down here. And for the resolution of the water droplets, we use the line pair as a standard. And if the resolution of a specific lens is too small, the line pair will combine into one after the projection. And so the smallest resolving power is the 2 pixels, which makes one line pair. And the definition of our experiment, the definition of our resolution is to measure that how many line pairs is in 1 millimeters, and the resolution is the camera. And for the calculation of the resolution, we use the resolution of camera itself and the times of the magnification of the camera. And we also use our experimental data, which is 1 line pair per 1 millimeters. And we can put it together so that we can get the resolution. And for the simulation of the punctuation operation, because the droplet we make may not be circle or symmetric, so that it will cause different reflective angle. And according to the spherical aberration, the outer part of the circle is close to the focal point of the marginal ray. So the focal length at outer part of droplet is larger with bigger incident angles, and so that the magnification is larger at the outer part of the circle. For the experiment, this is our experimental setup and equipment, and we use the concentric circle as our object to observe, because we want to know all part of the magnification. And we place it on a platform which is based on a micrometer that can change the distance between the glass and the object. Then the first parameter is the object distance. We change the distance from 2 to 26 millimeters. And the real object distance is from the top of the glass to the top of the platform. So we have to add the thickness of glass, which is 1.8 millimeters. And for this chart, you can see that as object distance increases, the object is closer to the focal point of the lens, causing the magnification more significant. And for some points that didn't fit the theory line is because the droplet we made might not be a circle or sphere, and the line may not be parallel. So it will cause a bigger error bar. And as the object distance increases, it matches the assumption of parallel race bar. So the points will fit the theory line, and also the error bar will be so smaller. And for the resolution, when the resolution of concentric circles increases with greater magnification as the object distance increases. And for the curvature of the radius, in the next parameter is the curvature radius of the droplets. And as the curvature radius becomes larger, the incident angle becomes smaller, and so it will cause a smaller magnification. And for some points that just the theory line is because the deviation was caused by the assumption and experimental phasing of water droplets as part of a sphere. And next parameter is the droplet thickness. And when the droplet is thicker, the focal point will be closer to the glass, and so that it will cause larger magnification. And the deviation here is caused by the shape of the droplet, which I mentioned before that the circle, the droplet we make may not be a circle or a symmetry. And this is the influence of size of the droplets. And the curvature radius and the droplet height change the incident angle of light rays of the object, and so it will cause a magnification difference. And for the curvature radius, it has negative with the magnification effect, and for the droplet height, it will have positive with magnification effect. And the next parameter is the order of concentric circles. And because of the spherical aberration, so they will have different parts. So for the different parts of the circle, it will have different magnification. And at the outer part of the circle is close to the focal point, so the magnification will be larger than the middle of the part of the droplets. And for this chart, you can see that when the magnification increases, we can observe more pixels per millimeter, so the resolution of the lens will increase. And for the conclusion, and for the first question of our main focus is how is the object magnified by the water droplets? And we model the magnification ratio as h prime over h. And while the object distance is smaller than the focal length, light rays are reflected because of the refractive index difference between water and air. So it will create an effect of a converging lens with a focus point on top of the water droplets. And for the second question, how do the properties of the droplet affect the magnification? It is that when the curvature has negative positive with the magnification, and the droplet height will have positive effect with the magnification. So the curvature radius and the droplet height change the incident angle of light rays from object and causing magnification differences. And for our third question, how is the magnification related to the resolution? And so the definition of our resolution is how many line pairs per 1 millimeter. So when the object is closer to the focal point of the lens, causing the magnification more significant. And when there is bigger magnification, the resolution will become bigger because we can see more line pair in 1 millimeter. And thank you.
Okay, now is the time for opponent to ask question.
Okay, so first I want to ask about, did you control the shape of the droplet?
We use the height to change to the.
Okay, let's discuss later. So did you consider the different resolution will also be affected? So what type of resolution did you use?
We define the resolution as with 1 millimeter. They will have how many lines?
Okay, I got it. So do you consider the refraction of the glass you use?
Yes, we consider about it.
Okay, so then what kind of magnification do you use? I mean, there may be depth and maybe angular magnification.
We consider about the angle of the magnification.
Okay, so you say in your syllabus, how did you measure the object distance?
The object distance, the definition of our object distance is from the top of the glass to the top of the platform.
Okay, so about the curvature radius. So how do you measure the curvature radius?
We control the same volume of the droplet, and then we will measure the radius of the droplets. So that is the radius of the curvature.
Okay, so you consider the droplet is a thick mirror or maybe a thin one?
When the thickness of the droplets increase, and then it will change to different length.
Okay, so do you know maybe the focal length of the droplet?
Yes, the focal length droplet will change.
Okay, I got it. So how about the spherical aberration? You consider the spherical aberration will affect the magnification or the resolution?
It will both affect because when the magnification increases, the resolution will also increase.
Okay, I got it. So you consider where the spherical aberration would be more, at center or at the edge?
When the object distance is more than the focal length.
Now you can finish your answer.
Okay. When the object distance is smaller than the focal length, then the outer part of the droplet will have bigger magnification ratio. And when the object distance...
Okay, thank you. Only short answer. So following is the preparation time for the opponent. Okay, it's time. So please, opponent, you can take this floor for up to 4 minutes, and any remaining time we will add to the discussion time. And please start. Okay.
Okay, so I'm the opponent.
Wait. So is it rebooking? Okay, so please start.
Okay, so I'm the opponent today. So we are talking about problem 2, the droplet microscope. So the report has been mainly talking about magnification and resolution of the droplet. So for theory of a report, the reporter uses Snell's law and consider droplet as half of an ellipse. And they talk about the focal length, and they also mention about the spherical aberration. And for experiment, there's a micrometer. They say that they use micrometer to control the volume of the water, and use a professional camera to show the picture. and the parameter, they different object distance and the curvature radius of the droplet maybe in the center and at the edge. And they try to use different droplet thickness and influence of the size of the droplet. And they have an order of concentric droplets. And for the strength of a reporter, I can say they have done a qualitative phenomena explanation and also had a good setup. So they can control the volume and also have considered the refraction of the glass. And they get a conclusion of the resolution and magnification from various parameters. And they explain about the path of light. And for suggestion, I can certainly explain more about measurement and how to control the shape of the droplet, and how to control the radius, and consider the chromatic aberration, and calculate the longitudinal and lateral magnification, and explain how to avoid the effect of spectral aberration, and consider the effort of the gravity on drop. So for the next discussion part, I will mainly about the setup, the method, and data analysis, and theory. And so I want to know that how reporter control the radius, and the method, the type of resolution and magnification using a different wavelength. And for data analysis, I want to know that how they measure the curvature radius and how it affects the resolution and magnification. Yes, so let's go to the discussion part.
Okay, please start the discussion. And
so first, could you turn to the page of your setup? I mean your setup of your droplet. Yes, with this page. So, could you tell me about the micrometer more?
The micrometer is used to change the distance between the glass and the object.
So this is not control the volume of the water?
The way we control the volume of the water is use the pipette.
So, I mean, you control the volume, but I didn't know how do you control the shape?
The shape of the droplet can be controlled.
Could you explain more about the shape?
Because the shape is depends on the thickness and the radius
Yes.
of the droplet. So when we think the same volume of the droplet, it will have different thickness and different radius of the curvature.
So you mean that the different shape will also affect the thickness, right?
Yes.
So how the thickness affect the magnification and the resolution?
When the thickness increases, so the focal point will and when the droplet is thicker, the focal point will be closer to the glass, and so it will cause a larger magnification.
Okay, so let's turn to the magnification part. So I want to ask about what type of magnification, just because there will be maybe the lateral and the depth magnification.
What do you mean the depth magnification?
I mean that you may have to consider the magnification just maybe just like this direction or this direction.
Yes, and at the experiment setup, we place the camera vertical of the object, which is here.
Yes.
So this is the way how we observe the magnification.
Yes. So what type of magnification do you consider you use?
Is the vertical.
Okay, I got it. So could you turn me to the resolution part? I also want to ask about the different type of resolution, just because there might be the optical or the image resolution. So what type of resolution you use?
Is the resolution we use is the camera's resolution.
Yes.
Yes.
So you mean it is optical?
Yes, it's optical and change to. Yes, and this is the definition of our resolution. Yes, the resolution is of the camera.
Okay, so, but I consider that this might be the pixels, maybe per inch. But the pixel per inch may be the image resolution. I mean, like this picture shows, it may be not the optical resolution.
For the optical resolution, please turn to page 30. And yes, there is the obstacles. Yes, there is the obstacles from the resolution.
So to summary, so what type of the resolution you use to summary report?
It's the resolution of the camera.
So the optical or the image?
It's the optical.
Okay, I got it. So could you turn to the curvature radius? A figure that shows the curvature radius of the edge and the center. The graph that shows.
You mean the figure model?
Okay, let's go to the 23. Okay, so how do you measure the curvature radius?
We use curvature to measure the curvature radius here.
Yes, maybe the different software or different method you use to measure the curvature radius. How do you measure that?
Yes, we use the software of tracker to measure the distance.
So can you consider that you just maybe draw a curvature circle?
No, we just measure the radius.
Okay, so but I would talk about the curvature radius. So why the curvature radius would be bigger at the left edge but not in the right edge?
It will be the same. Yeah.
But in your theory data, I can consider that the curvature radius of the left edge is bigger, but the right edge is the less.
And for the deviation, it was caused by the assumption.
Could you explain more about the assumption?
Yes, because the droplet we make may not be symmetric. So the left side of the droplet and the right side of the droplet will not be same. Will not be same, but it's similar.
So you consider the droplet is symmetric?
No, we assume that the droplet is symmetric, but actually it won't be symmetric.
Okay, so the magnification and the resolution will also be different, right? The different parts of the droplet.
Yes.
Okay, so could you turn to the spectral aberration part? Okay, so could you explain more about the spectral aberration, how it affects the resolution and magnification in your report?
For a spherical aberration, because the droplet we make might not be circle or symmetric, so it will cause different refractive angle. And on the art and chase 10 to 6 Yes, this is the simulation we make. And so for the outer part of the object, it will form a larger triangle at the place we observe. Yes.
Okay, so that the spectral aberration affects the resolution and the magnification. How it affects?
Yes, because it will have different refractive angles, so it will cause different magnification of different part of the circle.
Yes, so it will increase or decrease the magnification.
If the object of the distance is smaller than the focal length, then the outer part of the circle will have bigger magnification than the inner part.
Okay, so could you turn to page 11? So could you explain more about the F, the formula you use, the fixed minute or something?
The F is the focal length.
Yes. So the focal length, because the spectral aberration, the focal length may be different because the light not be so one focal length. So what's the focal length mean? Just due to the spectral aberration.
For the focal length, the different parts of the circle will have different focal lengths.
Yes. So how do you measure or calculate the F?
We first assume the droplet as a part of the circle, so that we can add a droplet height into the consideration, and then we can make the equation of the focal length here.
Okay, so how do you measure the alpha? Just because that may be the you imagine it?
Yes, measure it.
Okay, I got it. So I want to ask about how the light you put on the droplet. You mean I mean that you put the light on the curved part or the flat part?
Oh, we assume that the light is incident from the below of the droplet.
So okay, so you for a flat part to the droplet,
Yes,
right?
yes.
So how it affect if you use the curvature part?
It will affect.
So I mean how it would affect the resolution and magnification.
Oh. So you mean that we change the light?
Yeah, change the light, the direction of light from the curved part or the flat part.
Oh, if we change the light from the it will make the magnification maybe bigger.
Okay, so do you consider the diffraction of the light? I mean that because the resolution, the definition of the resolution may be the least instance that would be to us to distinguish. Yes, so do you consider the diffraction will also affect the light?
Yes.
Okay, so could you show me the parts?
Oh, yes.
Okay, so could you turn to page, you mean that the snail flow?
Therefore,
Yes. I want to know that how you measure the theta.
here.
Yes. How do you know the exact theta and how you measure it? Because that will be different in the air and in the water, right?
We don't actually measure it. It's just the model of the.
Okay, so okay, so can we turn to page 28? Could you explain more about this figure?
Oh yes, because I have mentioned about the separate aberration, so that it will cause different magnification of the concentric circle.
Okay, so you consider the center of the droplet will have basically no magnification, right? Because the value you show is about 1.
Yes.
Okay, I got it. So at the edge, because the magnification will be bigger due to figure aberration. So how about resolution at the edge?
Oh, the resolution is positive to the magnification, so the resolution will also increase when the magnification increases.
Okay, so that's my question. Thanks.
Okay, time is up. So I would opponent please present your summary.
Okay, so I asked the reporter about the figure aberration at the center and at the edge. So the reporter answered about at the edge there will be the higher figure aberration. Also, it will cause to the higher magnification and a higher resolution. And I also asked about the yourself. They use the pipette to control the volume of the water, but they didn't control the shape. So I would consider that there will still be some effect. And I also consider that because I asked about the type of the magnification and the resolution they use, and they answer that because they only use the optical resolution. But I consider that in their figure because there might be the pixels or the LP. So I consider that there might be image resolution. So I consider the report has to do more. And in yourself, I also asked about how to measure the object distance. And yes, and so. And I also asked about how to measure the theta, but the report just answered.
Yeah, time is up. So following is the reviewer to ask a short question to the opponent and reporter and opponent. Please start.
Okay, hi, I'm a reviewer, and I want to ask both of you, the reporter first, how will the water volume affect resolution?
On the curvature radius and the thickness of the droplet.
Yes, but if it increases, how will it affect?
If the curvature radius of the droplet increase, then the magnification will decrease. And for the thickness of the
I mean
droplet,
resolution.
the resolution is positive to the magnification. When the magnification increases, the resolution will increase too.
Okay, I consider the water bottle valid curvature radius, and then also I consider about because the bigger water volume would cause to the thick length of the droplet.
Okay, thank you. How would the opponent fix spherical aberration in this phenomenon?
I didn't know how to measure it, but I consider that they can know that because at the edge we have the bigger one.
And how would you fix the spherical aberration?
How do we fix the spherical aberration? How to fix?
Yes.
Oh yes, when the object distance is smaller than the focal length, then the outer part of the circle will have bigger magnification.
Okay, and do you consider the immersed depth in your calculation?
Which means the immersed depth.
When you go through different substance, the object and where you see might be different.
Yes, we have considered about it, but we didn't put on the report.
Okay, and how would you consider the mesh depth in this application?
Well, I consider they can just observe the center part of the droplet to know the depth. Yes.
I mean, the immersed depth.
Yes. Could you explain more about the immersed depth? What do you
If you look through different substance, you may see things and it's not in that place. It's due to refraction of the light.
Yes, so I said before, they can just look to the diffraction will be less compared to the age.
And what do you think is the best magnification definition to use in her experience?
I consider it the lateral because that due to the spherical aberration, that will be different magnification. Yes.
Okay, and what do you think is the best magnification definition to use? Because if you connect with the setup, what would be the best?
The best way to the magnification is this model. Here. Yes, we model the magnification ratio from h prime over h.
Okay,
yes.
And final question: will the magnification increase or decrease if it's in the reality and not the spherical shape?
Yes.
Would it increase or decrease if it's not? If it's real life?
What do you mean in the real
because
life?
you consider it a perfect shape, and what would the magnification be if it's in real life?
The time is already up, and you didn't finish the question before the time up. Okay, the following will be the preparation time for the reviewer. Reviewer, please deliver your review.
Hi, I'm a reviewer from Team Relativity. And here's a common statement. So if you look through a single water droplet, you can imagine it as an imaging system, and you have to investigate the magnification and resolution of such lens. So here's a summary of the report. So the reporter uses Snell swab to investigate how will light, predict how the light be inside the water droplet, and calculate the focal length, and then use the aberration simulation to know what would it be like. And in her setup, we use the lens, dropper, and the camera to analyze the experimental results. And for parameters, we use different curvature radius, calculate different curvature radius of the different volume and the object distance between the lens and the object. And here's the strength and suggestion for the reporter. So I think she has a complete quantitative phenomena explanation. And she also has a good definition for clarification in her report. And then I think she has a good experimental setup and a simple physics explanation. But I think she lacks some quantitative comparison in his theory and experiment in some of her different parameters. And I think she could improve on her measurement and then did not explain the experimental results well. And here's the strength and suggestion for our opponent. I think he also has a clear understanding on what's the different definitions for magnification and resolution. And I think he has a clear and short question asked. But I think he has a too short of summary of the reporter's report, and he did not tell us about what would he improve and his suggestion on the reporter's report. And so here's the discussion part. So the opponent asked, how do you control the volume of the droplet? And the reporter uses a pipette to control. I think it's a good way to control, but maybe there's another. But the shape is very, even if you control the volume, the shape is still hard. And the opponent say, how will spherical aberration affect? And of course, it's not a sphere, so it will have some aberration. But even though if it's a sphere, it will still have some spherical aberration. So I think it should take into consideration. And the opponent asked, what would the shape be like? And the reporter said it will depend on different parameters and it will form different shapes. But I think there might be still ways to control the shape and then be made the same in every experiment. And the opponent asked, which magnification do you use? And then the reporter said it uses a vertical camera to use. But I think it's very hard to actually use the vertical camera and the rocket droplet in the same place. So I think you should use angular magnification to consider the angle between the camera and the water droplet. And then the opponent asked, how do you measure the curvature radius? And the reporter said use Tracker to measure it. But I think maybe using Tracker won't be the most accurate software to use. Maybe use ImageJ or other software to get better calculate. And then the opponent asked, the focal length will be different on dropper. And the reporter said, if you consider it as a circle, you can calculate it. But I think in real life, there's still some difference between the perfect model. So I think she should tell us how to fix it to the real life. And then I asked the reporter if she considered immersed depth, and she said it's not on the report. And I think if she considered it, she should show us, and it's because it's important. And asked the opponent how would immersed depth affect, and the opponent said if you look at it in the middle, it won't, but I think there still will. And I think as the best magnification for a problem, the reporter said longitude, and I think it's angular because you need to consider the camera. And here, I think, is a missed point of the discussion. So I think you should consider apparent depth. Is this graph right here? If you look to different substance, the object and its actual, if you see the object and its actual place, might have some different places. I think you should consider if it's passing through different substance. And I think the aberration works on perfect spheres too. So it's not, yes, so here's the end of my.
Okay, thank you. This will be followed by the summary remark of reporter for 2 minutes.
And for the concluding remark, in our definition of the resolution is the number of the line pair in per millimeters. And we use the software tracker to measure the geometry of the water. And the magnification is positive to the resolution. And the curvature of the droplet will give the magnification negative effect, and thickness will give the positive effect. And the object of the distance is from the top of the glass to the top of the platform. And as the reviewers mentioned, the experimental data is very fit to our theory line. And this is for the spherical aberration. And so according to the spherical aberration, the outer part of the circle is close to the focal point of the marginal ray. and because the droplet might not be totally a sphere or symmetric. So magnification is larger at the outer part of the circle, and it will have a smaller magnification in the inner part of the circle. Thank you.
Okay, so I would like all three teams, the presenter of all three teams, to stay on the stage and be prepared to answer the question from the jurors. So any question from the jurors? Yeah, please. Please use the microphone.
Yes. So the reporter compared the experimental data and also the theoretical model. So it seems that in the final part you keep a linear relationship of the data. So I mean the theoretical part, and also your experimental part also gives you some deviation. So is there any meaning of the slope?
For the slope, is that yes, the first slope is when the object is increased, the magnification will increase.
So according to this, can you compare? So then your experimental data can be also linear fitted.
Yes,
So
it will almost fit the theory now. Yes.
No, I mean you can do a linear fitting of your experimental data. So what can give you the indication from this fitting?
Can you explain again?
Yeah, I mean he's asking what's the physical meaning of that slope.
Oh, the physical meaning of the slope.
Name. Something like a name or some physical property correlated to that slope.
For a slope, it means that yes, to this model, when the object distance is longer, then the magnification ratio will be bigger. This is the physics.
Okay, please.
The reporter said that the resolution, you use the resolution of your camera. So if you change the camera, so the resolution will be changed. So let me ask the reviewer, and then the opponent, and then the reporter. The reviewer, please. So will the resolution change if you change the camera?
I think I consider that it won't, because that if they just observe the droplet, not due to the camera. Mainly about the droplet resolution.
So I just want yes or no answer.
No.
And reporter.
Yes.
Okay. So if that's the case, so your measurement or resolution will depend on which camera you use.
Yeah.
Okay.
And I think it won't affect my camera.
Okay, any other question? Yeah, please.
Okay, so I have a question to the reporter. You measure the magnification in page 23, right? And yeah, but as we know that in page 20 that the magnification depends on the object distance. So how did you measure the magnification in page 23? Did you fix the object distance or?
Yeah. No. I turn to the parameters of the curvature radius of the droplets. Yes, we will control the object distance at 1.9 centimeters.
Okay, so if there is no further question, okay, please.
For the reporters, please turn to the previous page. Yeah, this one. You say you assume that the shape of the droplet is part of a sphere, but then to explain this, you could say the deviation is caused by the shape is not a perfect sphere. So did you verify that the shape of the droplet is actually a sphere or not?
Oh, the assume of the sphere will not cause any deviation.
I think you just answer. Did you check it or not?
Oh yes, we check it.
How you check it? I think that's the professor wants.
If you check it, then is it close to a sphere or not?
Okay, it seems like it's a sphere.
Then how do you explain this deviation using saying that it's not a perfect sphere?
Because the droplet we made will not be actually a wonderful sphere, so it may cause a deviation.
Okay, I think he's just commenting that you are making some inconsistency. But next question, please.
I just want a question for the reporter. Just turn to your ellipse about your I think page in the front page. You draw the ellipse. The ellipse of,
You draw an ellipse for the drop.
Yes, this one. How do you know that this is scalar? This is like this. It just extrapolate from this side to the other side. You write this as a dot, not actual shape. How do you know that you are element?
Can you explain it again?
Just, I just want to know why do you extrapolate this to be just a ellipse? Why not just a big one?
How did you confirm that your droplet is a part of the ellipsoid?
Oh, we will assume the droplet as an ellipsoid.
How do you sure that the process you take, how you sure that not you apply, you think?
Page 4. Yes, the surface tension according to the droplet volume and area, well, surface tension is gamma and gravitational force balance, and yes, it is the surface tension and it is the gravity.
Okay, I think that. Yeah. Okay. Very short question. Okay, please. Because
quick answer from a reporter and the opponent. You mentioned about the shape control. Do you have any recommendation? Just quickly.
I consider that the requirement is a wax.
No. Very short.
Okay, the wax and oil controls. Yes, I agree with the point.
Okay. So because of the time, so I would like to stop here. Then we proceed on the scoring part. Okay, seems all the scores were ready. So we start from the reporter's score, and I will read from my left-hand side to the right. So the scores are 7, 7, 7, 7, 7, 7, 6, 4, 8, 6, and 7. And the next is the score for the opponent, please. The scores are 7, 7, 7, 7, 8, 7, 8, 5, 7, 7, and 7. And the last one will be the score for the reviewer. Oh, okay. So, opponent, Professor Du is 5. 6, not 5. Yeah, previously it's 5. Now it's the score for the reviewer. Score is 8, 7, 8, 6, 8, 7, 7, 5, 8, 7, and 7. And I think we need some comments from the high and the low score. So for the reporter, I think the highest score is 8. So can you give some comments?
Okay, because as an experimentalist, I usually appreciate the efforts in the experiment. I know that there are some shortage in the analysis and in the parameter control, but I would say that there's already many controlled experiments here, and I can understand there are so many difficulties. So as a component reviewer, it's easy to challenge and to find some shortage, but I still appreciate the efforts in the experiment part. Yeah.
Okay, so I think Professor Du, please comment your low score.
The main point that I saw low is because it seems that the reporter did not actually understand the problem statement. Because when you measure the resolution is the resolution of the length of the droplet, not the camera. So if your result, your conclusion is the resolution depends on is the resolution of the camera, then it's totally wrong. And the other thing is about the theory and experiment. It is not very good. It's not optimized.
Okay, and for the opponent, I think we have 2, 8, and plenty number of 7, and the lowest one is 6, also from Professor Du. So can you also comment about the opponent?
I'm just a bit too harsh.
And we have two. One is from Dr. Li Bohan, and another is from, I think that's Professor Feng Yingbao. So can you give some comments? Yeah. About the opponent, you give 8. Okay. So, yeah.
I think even if I think you should determine that it is from this shape, not extrapolate and think that it is on the other side. I think it can be small.
Okay.
should consider this as a student, part of the student. You just get one parameter, but you get two parameters, A and B, and you have to extract these down to the other side.
I don't know if you get this point. I think Professor said that you just consider the angle theta, and from one value you cannot by calculation and get another two value. Usually you don't do that. You usually get another one value. So it seems you need another other parameter to put into your consideration, so you can say you have an ellipsoid. Yeah. And for the opponent, we have 4-8, and the lowest mark of 5, and plenty of 7, and 1-6. So about no, okay. So I think about there's a 6 from Professor Chen Zheng. Can you give some comments for the reviewer?
It's quite well from the jury, so that's why I count the score their rules.
Okay. And there are 3-8. Professor Gao Xianzong and Li Guohan and Lin Wenqing. So, Professor Gao Xianzong, can you give some comments about reviewer?
Overall performance, I think, of the reviewer is slightly better than the other two. So I want to make a distinction.
Okay, so it's fair, yeah. Okay, so I think we can close this round, and we will take a 10 minutes break. So please come back in 10 minutes. And during the break time, I would like to ask the 3 team to switch your seat. Thank you.
没什么架，就还没对关。然后豆沙。
我请试驾。
这手没请假，这个还关散。这手没请假，这个还关散。30个人。
他可能觉得他可以这种
很明显就是，当你今天相机用相机的那个解析度越大，它测出来那就不会影响。除非你的那个解析度测出来跟相机差不多，如果相机越大，就是他应该会，我不可能。 但是其实我不知道他3个包没有，他的
你看你没有来跟那个讲话，
好呗，哎，这是事实啊，这是赢的。
确定吗？
我们都知道，我还认识哎。啊，今天不认识。哎，我认识啊。黑土。
操！
谁啦？
我是吧？是谁？我是吧？其实我不知道他，我不知道他。哎，我知道哦。跟我讲。
为什么没有笔？今天没有2个。
我是一般没做。
我从来就没有，唯一根本就没有人要。就是家里哦，家里。哎，那你拿笔到吗？他没上台，
我这一场跟第5场，我第1场跟赵莎，然后在那个然后我
哎，我好像有一场玩完，所以你要来有啊？他说他要来。
我没有，
我真觉得吧，我觉得我你会比我烂。哦，那个，然后他不会讲，然后讲实验。
我觉得可以啊。
跟我当初不会讲 M， 然后在那边想半天。unit is
没有啦，我忘记了，
他走路。
那个你知道我那边对方是那个 Rocket， 我说the problem statement say that you should use water. Did you actually use 2 liter water to prove your thoughts?
我懂了，你真的喜欢你写，然后
不是，是因为我不知道要讲。
觉得水晶应该拿在，然后我点表演没人送。我在讲这个啊。要不要我？刚刚好，来下午的话，没有。对，这没有印象。下午中午有，然后礼拜4上午有。捷报写完吗？捷报写完了。我早就写了。不是上礼拜，你知道什么时候交吗？上礼拜1做，所以上礼拜2。
The break time is almost up, so I would like Sweeping to prepare. Yeah, only about 2 minutes left, so please call your team members back.
然后拍文就不别人是那个对，文是把我们那个发票里非常小的进，就我可以招10个人进来，然后拍1个。是不是我？不然我觉得你要把那个台调，把12小时来不敢放手写。没有，明年会有
然后那个限制那个 A 口啊，另外一个切纸的，它这样。好。自己做的。然后没有，我知道自己的然后所以我觉得
Okay, looks like all the members are ready. So I would like to start the second round of the final fight. The second round, the reporter will be the Excalibur, and the opponent is the relativity, and reviewer is Excelfire. So the problem to be presented is number 14, ruler tree. So we start from the preparation time for the reporter 5 minutes. Now we start now.
人都不见了。
so honorable judges and
start your report.
okay. Honorable judges and fellow competitors.
Wait a minute. The clock needs to reset.
Okay.
Okay, please start.
Okay. Honorable judges and fellow competitors, this is reporter from Pink South. Today I want to report number 14, ruler trick. So the proper statement presents that when you place the ruler on the edge of a table and throw a ball on it, the ruler will fall. However, if you cover a piece of paper on this and throw a ball again, the ruler will remain on the table while the ball bounces off it. So our task is to explain this phenomenon and investigate the relevant parameters. Here is the parameters I have done in my experiment. So our main focus will be on why the ruler didn't fall and how many force is needed to make the ruler flip. So first, let's look into the mechanism behind this phenomenon. When the ball hits the ruler, it will make the ruler lean over like this. So it will create a lower pressure area onto the paper. So the pressure difference will cause a force like this to make the ruler stay on the table. This physics is pretty much like a suction curve. Okay. And the downward force, we can calculate it by this equation. And it is good to know that A represents the area of the paper that comes up, not the whole paper area. Next, we analyze the torque in this phenomenon. When the ball creates an angular, when the ball hits the ruler, it will create an angular momentum. So torque at this moment can be calculated with this equation. Next, we consider about the torque from left part and right part of the ruler. Also consider about the air pressure and paper mass. So finally, we can know that if the counterclockwise torque is greater than the clockwise torque, the ruler will flip. Based on this formula, we can get the equation about the balance condition. However, there might be some potential complexity, like resistance force over bending of the ruler. Therefore, we have to consider the support coefficient. Here's how we know the support coefficient. According to beam deflection formulas, we can calculate the alpha with this equation. So after we feed our data, we can finally get the value of alpha. Back to our theory, because our goal is to know how many force is needed to make the ruler flip. So I control the S is equal to D and equal to half of the ruler. So finally, the critical force can be calculated with this equation. In our theory, we have to know the pressure difference, so we can calculate the critical force. Therefore, I place the cell phone around here, like this on the table, and use P-Fox to measure the pressure difference. You can see that when the ruler flips, that the pressure will experience a quick drop around here. After introducing our theory, here's our experiment outline. First, I will introduce suction model and ruler trick setup to measure the critical force and compare with the theory. Next, I will do experiment about other parameters. Here, I want to introduce what is the suction model. Because in my theory, I control the force arm equal to the resistance arm. So in my theory, the force close to my ball will equal to the F around here. But it is hard for us to measure the F in here, so we can use the upward tension of the suction model to measure it. Next, we use the force sensor and graphical analysis software to detect the data of the force. Next, I want to introduce how we use the real trick setup to measure the critical force. First, I use the fixed board to fix the initial height and control the position of the free end and also the paper. Here's how we get the critical force with ball. So I increase the initial height until the height is enough to make the ruler flip. You can see that the critical height is about 63 centimeters. Next, we can import this videos into Tracker
to get the change in the velocity and the contact time. So finally, we can get the critical force from this equation. However, I want to clarify that what is a flip, because sometimes the ruler will fall off the table, however, the paper still remain on it. And I think it is not a flip. In my definition, that the paper needs to fully leave the table like this. That I will record the data as a flip. Next, in experiment 101, we change the length of the ruler and use 3 different materials, including copy paper, drawing paper, and newspaper, each with different methods. So here's the experiment video about it. From the experiment result, we can find that if the length increases, that the critical force will increase. And drawing paper requires more force than copy and newspaper. And I think it is reasonable because in my theory that the mass of the paper and area of the paper also influence the critical force. Next, I use the ruler trick setup to measure the critical force of the same paper. Then we compare the 2 graphs. We can see that when we use the ruler trick setup, and the trend is very similar to the structure model. However, the value is lower than the theory, and I will discuss the difference later. In experiment 102, that we use 4 different papers with also same area but different width to length. Here's our demo experiment video. For the chart, we can see that if the ratio means the width to length is closer to 1, that the critical force will be up. Next, I use the ruler trick setup to measure the critical force also of the same paper. From the chart, we can also see that the trend is also similar to the structure model. However, there's no area around, there's no data around here. And this is because the ruler broke. Because the critical value is too big for the ruler broke like this. Therefore, we can get the real value of the critical force in this situation. Then we take drawing paper as an example to compare the structure model, ruler trick setup, and the theory. We can find that structure model is close with theory. However, the critical value is lower than our expected. And I think the reason of it might be the airflow around the paper. So I use 3D simulation to analyze the pressure under the paper. Here's a brief layout of my simulation. Here's the simulation video. We can find that we use 3 different speeds of ruler flipping to analyze the pressure on the paper. From the chart, we can also notice that if the ruler spins faster, that the space on the paper will have a lower pressure, contributing to a greater pressure difference. Next, we want to analyze different points of air pressure under the paper, like this. In stage 1, that the ruler flip will disturb the gas molecules around it, so there will be an oscillation in the air pressure. However, if the ruler touches the paper, that the low pressure pocket under the paper will form up. So there will be a quick drop in the air pressure. So I think the reason of the low critical value is that the ruler flip too slow means that this contact to the ruler, the contact time is too long. That there will be a low pressure difference contributing to the ruler easy to flip. So after experiment 1, we want to discuss other parameters. There I use different mass of the foam to do the experiment and see how the deflection angle be. Deflection angle means that how the ruler deflects. Okay. Here's a brief setup of my experiment. We can tell that if the foam mass increases, then the deflection angle will also increase. And also, if there's the height beyond the critical value, that the deflection angle will be stabilized like this. However, there's no data around this situation, and this is also because the ruler just flipped. The height is too high, and the ruler flipped, so there's no deflection angle. Next, I want to discuss the placement of the paper. Okay, so this four paper is the same area, but these two didn't flip. So this can prove that the area is not determining how the force on this. And I think the main factor is because the distance around here. Because as this didn't flip, that the distance is bigger than these two ones. And I think this is because the torque around here will also make the ruler remain unstable. So in my conclusion, that's back to the proper statement. We use pressure difference, torque analysis, critical force to explain this phenomenon and investigate on the relevant parameters. So first, we compare the suction model and ruler trick setup. We can find that if the length grows, the critical force also increases, and the joint paper requires more force than the other two materials. Next, we also compare the ratio of the width to length. We can see that if the ratio is closer to 1, that the critical force increases. And ratio closer to 1 means that shape is close to a square. Okay. Next, to know when there is a low critical force, we use the simulation to measure the pressure on the paper. And my conclusion is that the flipping speed is lower, so the pressure difference will be lower. Therefore, there will be a lower critical force. So this is my experiment. Thank you.
Okay, thank you. So following is the question from the opponent. Clock? Wait a minute. The clock needs to reset. Yeah, okay, please start your question.
Okay, so first we can turn to the problem statement. Yes, at this problem statement, it has mentioned the ruler of flow. So do you definite the flip as also the paper will flip? So are there any concerns?
Yes, I think a flip is one of the fall, and the fall does not include a flip. I think maybe the friction.
Okay, I understand. And so the next question: do you use the same paper every time?
Yeah, because if we compare the other parties, I control the paper.
Okay, and next question: do you think the shape of the paper will affect this phenomenon?
The shape of the paper?
Yes.
Oh, you can get the conclusion from the ratio of the paper. Okay.
Understand. And for the next part, that if the paper is very huge or very hard, do you consider that it will also affect the phenomenon about how the ruler will flip?
Yes, because drawing paper is harder than the other two materials, so we can...
yes or no?
Yes.
Okay, understand. So do you consider that there's a critical angular velocity of how the paper will fall? Because from the flow 3D simulation, it seems that we discussed about the angular velocity. So like from a flow 3D, you have discussed about the angular velocity will cause different flip, right? Different conditions.
Yeah.
So then do you consider there's a critical angular velocity that will be discussed?
You mean what the critical velocity will cause?
Yes. Have you discussed this in your experiment?
I didn't discuss this in my experiment.
Okay, understand. So do you consider that the low pressure area is a chaotic or a static, unsteady or unsteady flow?
I'm not sure I can get the conclusion from my experiment, and I think this might be not chaotic.
Okay, I understand. So do you consider that the Bernoulli's principle will fit in this phenomenon?
I think the airflow under the paper will affect this phenomenon, but Bernoulli's principle we can discuss later.
Okay, I understand.
Okay, thank you. Time is up. So, opponent, you have 3 minutes to prepare. Yeah, okay, time is up. So, opponent, please present your result. Clock, can you switch and reset? And can you go to the next one and reset that one at first? And then back here, yeah. Okay, can you reset the clock so he can pass full time? Okay, please start your present.
Okay, so good morning, honorable judges and listening fellows. I'm the opponent from Team Relativity, and today I'm going to oppose problem number 14, ruler trick. And here's the problem statement. It mentions to place a ruler on the edge of the table, and if the ruler fall off the free edge, the ruler will fall. So first we have to discuss about how the ruler falls at the definition, because the reporter only discussed about the condition of both the ruler and the paper will flip. But I consider that there's also some conditions that only the ruler will flip, and secondly is that, however, it covered a part of the ruler with a piece of paper and repeat the third. Then the ruler will remain on the table while the ball will bounce with it. So we have to explain this phenomenon and investigate the regular parameters. So as the summary of the report, we considered that the reporter used a torque calculation to discuss about different torque of the air pressure, the paper, the ruler, and the ball. And second is the air pressure calculations that we concerned to use flow 3D modeling this theoretically. And third is the support coefficient to understand, clarify about different elasticity of the ruler in boundary conditions, and fourth is the structure model and compare with the true conditions of the ruler trick. And first is the deflection angle to measure how the ruler flips. So consider this is discussed about the critical angular velocity. And for the experiment, they use the parameters of the paper length, paper material, mass of the ball, paper placement, shape, and drop height. And as the setup, they have used force sensor, ruler, ball, and ball dropper to concern this experiment. And as for the reporter, we concern he has a complete qualitative phenomenon explanation and have a good assumption for the sucker model, but there still being made some adjustments because the air pocket shape may affect this phenomenon clearly. And next will be the discussion we further will be discussed. And thirdly is the simple basic explanation and have a good qualitative understanding about the problem statement and the conceptual clarification. But as a suggestion, they consider that the match theory model experiment because the structure model will be adjustment that we have to concern in later discussion, because there will be, I think there will be several conditions about how the ruler will flip. And as for, we consider that as for parameters which affect the result as the shape of the paper and the thickness and size of the paper as extremely hot, extremely huge and extreme minimum conditions. And also the flow 3D does not match the model because after the assumption there's some difference between the conditions because the paper in the flow 3D is floating up to the ruler. And we're concerned that air pocket shape should be concerned in this experiment. And the next point in the presidential concern is the quantity calculation of the air pressure because the reporter has used low pressure to concern in the air pocket. But we're concerned that firstly the adiabatic conditions, and secondly is that it may be chaotic, is the steady flow or unsteady flow. And second is how to fix the model and how to fix the result. And third is the critical angle velocity discussed of the ruler. Okay, and for the discussion, we concerned that there will have some simple physics explanation about how the air pocket in this phenomenon will affect this because it's the most important part that will be discussed. And there will be some kind of modeling about the reporter should use the Bernoulli principle and the definition of flow and also the support coefficient and the condition of adiabatic that concern in the air pocket. And for the experiment, we concerned that the same paper would also affect the shape of the air pocket, and the second model discussion concerned with the ruler trick condition, and also the deflection angle was concerned with the critical angle velocity. And next will be the discussion.
Okay, please start your discussion.
Okay, so firstly, can you turn to the problem statement? Yes, this page. And so at this part, it had mentioned the ruler will fall, but at some conditions it will remain on the table. So how do you definite the fall in your conditions? Can you clarify again?
Okay, so in my definition, I define the definition of flip, right? And I think there will be another condition of fall. Can I use it?
Yes.
Also, definition of. So I think if there's a table, okay, and there's a paper, sometimes the rule will be like this.
Yes, I understand.
Okay, so and the fall will depend on the friction around here.
Yes. So do you consider the friction?
Yes, I think this is one of the conditional fall, but in my experiment, I want to specialize in the flip part. So just yeah.
Okay, I understand. So in your modeling that you're concerned that here's an air pocket like this, right? So do you concern is an adiabatic conditions, which is isolated with outer conditions? Like, which means that in these conditions, it will the air flowing before the ruler will cover. Do you consider?
I think just when the ruler flips right, then there might be some hole around the paper. So at that point, that the air will flow into it. And you just discussed about the Bernoulli's principle, right?
Yes.
Just can you tell me, basically in general condition, can we just?
So sorry,
I think concept of the Bernoulli's principle that if the air flows faster, there will be a low pressure at this area.
Yes.
Yeah. So I think Bernoulli's principle, because there's air flowing to it, that the person sometimes we can use Bernoulli's.
But sorry, you concern this is a steady flow?
Steady.
Because if you need to use the Bernoulli's principle, you have to concern that the air pressure in this will be a steady flow. But in your experiment, we didn't concern that you understand whether it is a steady flow.
Yeah. So I didn't just. So I think Bernoulli's flow might be a fact, but it won't have a fact match. So I think just airflow, the max factor of the airflow is the time of the airflow, because when the ruler flips slower, that the airflow will have enough time to flow onto the paper. That the pressure under the paper will be close to the pressure above the paper. That the ruler will be easy to
flip. I understand. So the next question is that in your consideration, you concern that there's a friction. So how do you think the friction will affect this phenomenon?
Yes, okay. So just like I say, that there's a friction, right?
Yes.
And there's also the mass causes the force of the ruler, right? And we can just divide it the force like this.
Yes.
And I think if this force is greater than the friction, that the ruler will fall.
However, do you consider your concern that there's air pressure?
Okay, just I want to focus, in my report, I want to focus on the flip condition. So I think our discussions are supposed to focus on the report.
Okay, but I just want to, okay, so in your conditions, you have mentioned that it will be the fall from, you drop the ball from here, right?
Yeah.
It will have to have an air pocket. But you're concerned that it will throw, because the problem statement didn't mention about how the direction of how the ball will fall. So you're concerned the direction it will throw the ball below the ruler tree, below the ruler.
I also think that it is an interesting point to discuss because I want to focus the discussion on the research on my report. But I also think.
But sir, I just want to discuss about this condition.
Okay.
Can you tell me? Let's discuss about this condition. You're concerned that the air pocket will also affect, or you don't think that there will affect the air pocket?
Oh, okay. So I think if we throw ball, you mean throw ball from
below the
rulers?
Yes.
I think this is out of proper statement.
Sorry, can you turn to the proper statement? It just defined that if you place a ruler, it just remains that throwable for the
proper statement didn't define we throw a ball from side or throw a ball from.
Yes. So you're concerned that in this condition, if we throw a ruler from below the ruler, it will form an air pocket?
I think that it's just interesting, but in my report I didn't discuss
sorry, I mentioned that you wanted to discuss. Okay, it's okay.
Okay. So you just in the short question, you mean chaotic, right?
Yes, I mentioned that you're concerned it's a steady flow or unsteady flow.
Okay, so I want to answer that. Okay.
Yes.
So first I want to define a chaotic, and I mean this first there's two initial conditions. If these two initial conditions will finally lead to a regular consequence, that the consequence is the same. I think this is not chaotic, just about airflow. So, and what's your definition about chaotic?
I'm concerned that because can you turn to the full 3D simulation? Sorry, but at this part, can you turn to the page to discuss? You can see that there's some animations at this part. Yes. At this part, you can see that if the ball hit the ruler, if the ball here will have some oscillate, which causes the air pressure to be chaotic, and also it means that the air pressure is high pressure and low pressure, which causes the pressure to push, then the air will expand into. So I consider it will be a chaotic condition. So I think it won't be considered to use the Bernoulli's principle that we discussed further previously.
So you mean if there's oscillation, that it will be chaotic?
Yes.
Also, your definition of chaotic is oscillation.
I didn't understand that. I'm concerned that it's not the oscillation. I mean that because of this oscillation, the air molecules will be just like mixed and
yes. So I want you define. What's your opinion about the chaotic and about it?
Yes.
So can you define your
sorry, we'll just focus on the discussion.
Yes.
So yes. So at this part, you're concerned that the angular velocity is one of your parameters, right? Or only a single angle?
In the simulation, this simulation, I just want to demonstrate that I want to adjust the misprediction in my previous experiment. And
yes.
I think that our experiment data not match with our theory, so I use the simulation to find the reason.
But can you turn to the page that you have simulated both a schematic about a placement, a ruler, and a paper that just you had to introduce about the flow 3D? Yes, this page. Okay. So at this page, you can see that this simulation, the paper is suddenly float up to the surface of the table, and it didn't contact with the ruler. So which means that in your definition, there will be air pockets, so the ruler will be like this, and also it will have a volume here. But in your concerns that it just doesn't totally touch the ruler, so how do you concern that can you tell me some adjustment if you use the simulation here to discuss, or are there any adjustments in this condition?
I think even the paper just had directly contact with the ruler, that this simulation also can prove that the velocity of the ruler flipping will cause the low pressure on the
Yes, but why don't you do this as one of your parameters? Because you are concerned that this will affect this phenomenon.
Because this is enough to prove that the space under the paper will have a lower pressure. This is enough.
Okay, I understand. So can you turn to the page of the critical angle that you've discussed about how the ruler will flip? critical angle that you have somehow discussed about the critical angle of your experiment? Some angle, just the deflecting angle.
Of deflection angle?
Yes. Yes. So in the concern, you can see that at this part, it will actually seems like this. This is the paper, and it will have an angle like this to the paper like this. You understand? Like this, right? So it means that here is the low pressure area, and which has caused the high pressure area. So in my concern, I considered that before. The reason why the ruler will flip, and the reason why the ruler won't flip, is because that firstly, is because like you understand that if before the air has flows into the into the pocket, the air pressure, because the high low pressure just push it and just prevent the airflow to push it. And so, do you concern that, are there any experiments to prove, do you concern that if you add some holes below the surface, which will cause the phenomenon to not happen from the proper statement?
Oh, okay, so you mean just if there's some hole under the table?
Yes.
The table? Oh, I think if there's some hole on the table, that the pressure above the paper and under the paper will be the same. So I think that
won't affect, right?
That the phenomenon won't happen.
Okay, so which means that the main focus on this definition will clearly become a bit definite about before the air flows into the air pocket, the high pressure and the lowly pressure, which relatively concerned, will just first be pushed down the water, pushed down to the area of this, which caused it to remain stable. Do you agree? Do you agree?
You mean
Time is up.
Okay, I understand.
So, reporter, you want to answer that or not? You can answer shortly.
Oh, okay. So I think we don't have to just limit the time just before the airflow flowing, because.
Okay. Thank you.
Okay. So.
Wait a minute. Yeah, please give your summary.
Okay, so here will be the summary of discussion. Firstly, we have definite about how the flip or the fall from the proper statement. And for the experiment of how the report has concerned, he only concerned about the condition of how the ruler and both the ruler and the paper will flip. But I consider that in some normal condition, because there will be some critical angular velocity which cause that only the ruler will flip. And also, second is the airflow steady inside the paper, and I consider this is an important part which discussed about the main focus. And thirdly, how will the friction effort result? And fourth is that what will happen when the ball is from below, but the reporter didn't concern these conditions, but from the proper statement, I concern this will be one of the parameters. We expect the air pocket, which is the main focus that will be discussed. And fourthly, the angular velocity will affect the results, and I also consider this also will be an important parameter, because that from the simulation he had concerned that the angular velocity will also affect this phenomenon, but from the experiment he didn't concern, so I suggest that the reporter can consider it as an important parameter, which also will connect it to the critical angle.
Time is up. Sorry. Okay. Reporter, please be ready to answer the question. Opponent and reporter, please be ready to answer the question from the reviewer. Okay, please start.
Okay. For opponent, how well do you think the friction acts in this phenomenon? Did you ask about it?
I concern that in some conditions that because of the ruler like this condition, that the paper, the ruler will contact with the paper. So before it falls, there will have some friction. And also because if the paper is really hard, that would cause the friction and concern will be extremely
So
big.
you only consider the friction between the paper and the ruler?
Sorry, from the discussion we also have considered about the relatively pressure difference and also...
No, I mean the friction part.
Yes.
So, okay. And what do you think about the air pressure or pressure gradient?
Can you explain more clearly?
Like the outer part of the paper and the inner part of the paper's pressure difference.
I'm concerned that it's before that the ruler will have a certain, in a very short time, it will flip, which causes the paper relatively different to the other paper, which causes the air pressure highly pushed in, and also in the air pocket area.
Okay, thank you. And for the reporter, what do you think is a critical factor that depends whether the ruler will flow or not?
I think just
the most important.
Most important will be the pressure under the paper.
And what do you agree with him?
I'm also concerned it will be how the ball has fall with torque.
Okay. So if there has two situations, one is a heavier ball released in a lower height, and a smaller ball released in a higher height, and when the gravitational force they provide to the ruler is the same, what will the result be like?
I think the time that the ball contacts the ruler will be important.
I also agree with the reporter, and also concerned that the contact area will also be important.
And what do you think the contact area will affect?
Because if you mean that in this condition, maybe this will all affect in this condition, but also at this point it just affect at this point. So which caused that maybe the torque which hit in the part will also affect because of the impulse.
Thank you. For a reporter, did you check the motion of the ball that bounce of the ruler since the problem statement says bounce of it?
Yes, I have to experiment about the bounce off velocity, and I use the bounce off velocity and the initial velocity that I can calculate the change in the velocity, that I can calculate the critical force. So I have to do that.
Okay, for your opponent, do you think the motion of the ball bounce off the ruler will affect the result?
I consider that it's firstly the first moment about how the ball hit the ruler affect this phenomenon. So before the bounce of the ruler, I consider that will not be the main focus of this.
Okay, and how do you think the ruler's ratio that's under paper will affect
Sorry, time is up. You didn't finish the question, so there is no answer need to be delivered. So next will be your prepared time for 2 minutes. Okay, please present your review.
Albert, Juris, and fellow competitors, I'm the reviewer from Team Excel here, and we're going to review the number 14, the ruler trick. The problem statement said, place a ruler on the edge of the table and cover paper with it. When the ball falls on it, it will remain still on the table. So due to the problem statement, we will mainly focus on the critical conditions and why will the ruler remain still. And this is the summary for the report. He mentioned that he shows 2 videos of whether the ruler fall or not in his phenomenon. And for the theory part, he said about the torque that explains the balance of the ruler, and for the experiment part, he did several parameters including the releasing height of ball mass, and then he did a conclusion. And for the pros and cons for the report. he shows clear observation video, and then he explained the airflow, which I think, and the air pressure on the paper, which I think is quite good. And for the lag, he didn't discuss about the friction, which I think is the most important phase at the first. And he didn't test on different shape of paper. The next is a review for the opponent. He asked about the parameters about the shape, and he discussed about the setup and the simulation, which I think simulation is quite interesting. And for the lag part, I think the airflow velocity into the space under the paper is quite important, but they didn't discuss about it. And he didn't have a good time control. And the first is a key discussion about the Bernoulli's principle. The opponent accepts if the flow is the flow a static flow, and reporter thinks that it's not chaotic. But I think that I suggest that if a reporter really wants to use the Bernoulli's principle, then she should consider the energy loss of the airflow under the paper. And also the friction part, the reporter didn't consider the friction, but I think when there's no paper on the ruler, the friction will affect whether the ruler will go or not. So when there's, so we also need to consider the friction between the table and the ruler. And for our question, we asked about the critical factor of this phenomenon. We think that the critical force is the most important part, and the opponent thinks that they should consider the bow, and the reporter thinks that it's the pressure on the paper. And last is the motion of the bow. We think that when the bow falls on the ruler, if the bow bounces off it, then the ruler will remain still. But if the bow didn't bounce off and just fall off and collapse the ruler, then the ruler won't remain still. So the motion of the bow is also important. And for appointment, for the theory part, I think they could consider more critical factors despite the forces. And for the parameters, they didn't discuss about the elasticity of the ruler, which will affect the result, and also the mass of the paper. And for the experiment part, they didn't consider motion of the bow, which I think is quite important, and a ruler ratio on the paper that will affect the critical height of the experiment. Thank you.
Okay. Now is the concluding remark from the reporter for 2 minutes. Yeah, please start.
Okay, this is concluding remark from Pink Salisbury reporter. And during the discussion, we used low-pressure token to explain the phenomenon, and also introduce the torque analysis, equation of the critical force, and suction model to simulate. And also, we also talk about the full 3D simulation to explain the experimental results. For experiment, we also I use different lengths of paper, different ratio of width to length, different mass of the paper, and different material of the paper. Here's the result. We can find that it was suction model. If the ratio is closer to the suction model is closer to our theory. However, the real critical value is lower than our theory. And when the length of the paper increases, that the critical force increases. If the ratio of the length to width increases, that means the square is similar to a square, that means critical force increases. And also, finally, if the mass of the ball increases, that the deflection will increase. So this is about discussion part. Then talk about shape of the paper, suction model, Bernoulli's principle, and I think there might be some problem there. And also talk about the definition of chaotic and the simulation of full 3D. And experiment part, we define the flip and the flow. Also consider about the shape of the paper and deflection angle, the direction of a ball falling, and if there is hole on the table, what will happen. And also talk about the friction between the ruler and the table. Also talk about the bounce velocity, and I do the bounce velocity because in my tracker part, I have to know the bounce velocity that I can consider about the change in the velocity. And I think that the opponent says he didn't think that bouncer velocity is important, I think there may be some problem there. So this is my concluding remark.
Okay, thank you. I would like to ask all three presenters to stay on the stage and ready to answer the question from the juries. And please be sure your microphone is on. Okay. Any question? No question? Yeah, question, please.
What's the point of making those
Oh, sorry. Okay. You ask about whether the flow of the hair is adiabatic or is it follow early principle? Early situation, I think that's what you mean, right? Why you mention that?
Firstly, because I'm concerned that the Bernoulli principle won't affect this phenomenon, so I'm concerned that it is still adiabatic condition.
It won't affect what you ask.
Yes, because I'm concerned that
you're testing the reporter's knowledge.
Yes, in some other position from this policy.
Okay, okay.
Any other question? Yeah, please. Dr. Du. Are you first?
Okay. For this experiment, I think the initial condition is very important. So I want to know, you three guys, how to prepare the paper on the desk. Because you paper on the ruler, right?
Yes.
And do you prepare something for the paper on the ruler? What kind of condition you prepare?
Oh, so you mean placement? For placement of the paper that, can you do an action model? Okay, so before the placement, because I want to use action model compared with the ruler setup.
How you prepare the initial condition?
Yeah.
Please, please limit your answer to that.
Okay, so the ruler, the end of the ruler will be in the middle of the paper.
And do you prepare some case for the paper? I mean, you just put on the paper on the desk, just it, and then the opponent will review.
Okay, so firstly, I consider that this condition is quite well, but I also consider that from different place of the condition of the placement of the paper from different area also cause the air pocket condition to affect, because I consider that the air pocket will be the important factors.
Review.
So you mentioned that the paper on the ruler, just the paper?
Yes.
And we think that we need to know the certificate position of where the ruler put on it. And also, we need to change a new paper since that after several experiments, the paper may have some wrinkles on it. So it will lead to a easier to match the paper.
Okay, thank you.
Yeah, okay, Professor. And then Professor Fu.
Can you, reporter, can you show the last experimental data about the angle?
Okay.
The data, the angle, the last, yes, this is the graph. So let me start with the reviewer. So there is a value, right? Is a saturated value. So how does it relate to the impulse? Because in your critical force there is a delta T. The delta T that angle, if you have a higher sexual straight angle, will the delta T increase at start with the reviewer or maybe opponent?
You mean the impulse and
the impulse, because you measure there's a delta T in the force, critical force.
Yes.
Okay, and this is a theta, a saturation theta. So is there any relation between them? Yes or no?
I consider yes.
Yes. So it increases or decreases with the angle.
I consider that if the impulse speed increases, the angle will also increase.
Okay.
Yes, I agree with the opponent that impulse increase, that degree will increase.
And I also agree with both of them.
And question?
For all, in your experience, how to show this ruler trick more surprise? The bounce off is very high. You need to think the important factor.
Okay, so you mean the ruler will bounce off? Okay, so I think
the ball bounce to the highest situation.
Okay, so I think that the ball bounce off is because that the ruler will bounce off from this situation, because the
most important factor,
bending of the ruler. Bending of the ruler, that it will be an extreme like bounce off. Because the ball bounce off it and the bending of the ruler will have a force that make the ruler.
Okay, I also consider the elasticity of a ball and a ruler.
Which one? You have two, ball and the ruler.
I would choose the ruler.
I also consider that it will also affect the support coefficients as before I considered, but moreover I considered that the bounce of the ball before
one factor, most important one.
You mean?
Answer ask most important factor, so you have already three. One factor, most important.
Impulse. I consider it is the ruler.
Okay, so if there's no further question, we move on to the scoring part. Okay, looks all the jurors already determined their score. So we start from the reporter. The scores are 8, 8, 8, 7, 8, 6, 6, 8, 6, 7, 7, and 7. And the score for the opponent are 7, 7, 6, 7, 7, 7, 7, 7, 7, 6, and 7. And the scores for the reviewer are 6, 7, 8, 6, 7, 7, 7, 5, 8, 7, and 7. Okay. For the reporter, we have a little bit distribution. Several 8, several 7, and 2, 6. So I think it's a little bit even. So any comments to be delivered? Yep, please. It will take something like 3 seconds.
I think the reporter do the experiment, but he spent little time in discussing how the ball impact the ruler. And then what happens later on. I think this is a very special initial condition. So you should have to consider this more. Address all the necessary results. And there are lots of people anything for bounce off or just follow the lead and then turn the ruler, etc. We should have considered this more the right.
Any other comments? Okay. And for the opponent, there's an more even score distribution. We got the 2, 6, and all the rest are 7. Any comments about the opponent? Yeah, please.
Question for the opponent is to discuss about what has been done first. That's the usual way we discuss science. Thank you.
Yeah, I think that's a very important point. And for the reviewer, we have 5 and 2, 6, plenty of 7 and 2, 8. So, any comments about the reviewer's performance? Okay, yeah, that's okay.
Especially for the reviewer, because the reviewer sitting there had so much time to watch. So usually, the 5 is not bad.
Yeah, okay. Yeah, actually, 5 is not bad. Yeah, 5 is in the average score. Okay, so I think we can close the this round and take 10 minutes break. So please come back and be ready before at 10 minutes.
器这样。
我们是这样。我讲到第几呢？就是那个
我们一直拿
他的节目讲的
是区段的，然后我的题目我只做2次，我们总共做5次，1次是对语，然后2层次都是。大型发生版讲了1次，然后那个摄像已经讲了1次，然后2次都被特别来引起来。就是没有理过，因为理论不出来。
班长跟我。
但我没有上过他的课。
就是找他的课，然后就是我那个他那时候是我教的，然后他说机械叫发出来声音，这机械人
我回去，我稍微不一定。
这是效果。越聊越教
还是你不用教了，你直接交给我另外是这样。我就是不想说要2个人。
今天啊。
就那个欧大司机啊。
我小电脑课就要教了。
明天以后你拿什么讲？
这不是这样写吧？
这我本来想说，这完全我。
你还可以去分。反正就是因为我的理论讲的超级，然后他已经跟我说，他要把的质量会没有想到会有差别，但他是不会，他们是不知道鸡跟饭的。
反正你要写，你不能当这个。你有什么东西，那个业余就是把什么东西都当评审，所以这个一般啥是另外一边都不能猜。这边都已经
你那个初中没有意义，那个连饭都不知道。
不是这国中高中没在，我是说，他是要基因大概是基因就是像我基因来讲，对。
对啊。
为什么？为什么在后面我被变烂？为什么？
你不能把这个为什么？你不要抄别人。
为什么？
我
主播你应该到了。 而且我还有提供是，还有说那个速度等于那个多少？
你这照别组，
然后太好了，他说我去，他说我去人家的时候才所以他这比较细。
我维基百科是要说，你觉得我觉得大，因为我答。然后对，我听到你讲一条维基百科的，
但是我要讲的维基百科只是说，
不行，因为你不能在维基百科
真的不要。这个我跟学生当我这个是。我就只在维基百科上面查一查。
你这样跟他说，你要跟他说，我从哪一版的读物课本里面看到，你不要跟他说维基百科。
读物课本就不用讲这个。
那你就跟他说高中
课本里面只有讲重点，读物里面只有讲重点，讲。
不然那个在大学的哪一本课？不要，绝对不要做维基百科。
然后我说，可是这个真的比较蠢，这个没有，就是然后我那时候
Okay, I think all the jurors are already back, and the reporter team, opponent team, and reviewer team are all in seat. Okay, so let's start the last round of the final physics fight. The reporter will be the relativity. Opponent is team Excel-Fire, and reviewer is team Excalibur. And the problem to be reported is number 10, wet scroll. So we start from the, oh sorry, magnetic gear. I make the wrong name. The problem is number 10. Magnetic gear. So let's start from the preparation phase for 5 minutes. Next one. Yeah. Okay, so let's start the presentation. Okay, you have 12 minutes, please.
Hello everyone, I'm today's reporter Tony Chen, and I come from Team Relativity. And today I'm going to talk about question number 10, magnetic gear. The problem statement of the magnetic gear is take several identical feature spinners and place them side by side on a plane. And when you rotate one of them, others will rotate only due to the magnetic field. You need to investigate and explain this phenomenon. And here's my main focus. First is the maximum speed difference for accelerating or decelerating about spinner. And second is the energy transfer rate of a spinner. And third is the maximum driving torque between a spinner. So the first one is gear properties. And an observation, it can be observed that gears mainly exhibit two characteristics, torque and transmission. So at the first part, I do a transmission observation. And at this part, I do the observation about the arrangement of the magnet. And in this part, I do the attraction and repulsion of the magnetic arrangement. So in the attraction part, when I try two bigger spinners, it's easy to free rolling. But when I try three spinners, when I drive the non-stable pair or a stable pair in the three spinner part, it won't rotate. But another one is the repulsion. When I try the repulsion as the arrangement of my magnet, and the two feature spinner part have more stable than the attraction, and the three feature spinner part, it will rotate. So based on observation, I give some analysis of the attraction, and because the magnet is not continuous, so the stable situation is limited to 3 points, so it makes this phenomenon less stable. And another is the repulsion, and because the magnet is not continuous, so you have a greater distance to let it in a stable condition. So I choose the repulsion as the arrangement mode of a magnet. So next observation is the speed difference, and when the speed difference is in a certain range, it won't free rolling. But when the speed difference is too large, it will free rolling. So next part is my final observation about energy transfer. My magnetic gear also experiences energy transfer and energy loss in losses energy continuum until stop. So next part is the second part about distance. So first I define when a circle is traced by the feature spinner and is tangent to each other, I define it as 0 centimeters. Any closer distance, I define it as negative values, and farther distance, I define it as positive value. So here's my setup about distance. And first, I found the minimum distance of the magnet here is about negative 0.25, and under closer distance, you attract each other and stick together. So next, I use the motor to let it spin continually, and I found that instability of the transmission phenomenon is began at 3 centimeters. And so I use pen to let the rotation speed slowly, and I found that the maximum speed, maximum distance difference is around 4.5 centimeters to 5.0 centimeters in my experiment. So based on the experiment, I gave some analysis of these things, and when the magnet is too close, the repulsion was smaller than the attraction, so the two magnets will attract each other and stay together. But when it is too far, the magnetic field will too weak and provide too small torque, so it won't rotate. And next part is third part about maximum driving torque. And to determine about this is to determine the stepping phenomenon boundary conditions. And the stepping phenomenon means when the external torque is bigger than the maximum driving torque, it will happen a free rolling phenomenon. So what I need to do is I need to find out the boundary condition of the stepping phenomenon. So because torque is caused by magnetic force, so I first consider a magnet shape as a fan-shaped magnet to calculate purpose. And after I consider it as a fan-shaped magnet, I can get equation 1 about magnetic field. And after I put my experiment data into this equation, I can get equation like the blue one. And because we have 3 magnets, so we need to sum them up, so we can get equation 2. And when I put equation 2 in the decimals, we can get a magnetic field to distance relationship. And because we have magnetic field in hand, so we now can calculate the torque of our driving gear, and it can be expressed as these equations. And where J is the surface current and equals to M, and M is magnetization intensity. So because the theory distance is from the center of a visual spinner to a magnet, so the distance from the negative 0.25 to 4.75 centimeters in the theory is 5.25 to 10.25 centimeters. And we're not considering the 5.25 to 5.5 centimeters. So here's my setup about torque. And I use a force sensor and make it vertical to the visual spinners. And what I do in the variable is I change the distance between the 2 spinners, and I can measure the maximum driving torque of this. So I use linear graphical analysis and sales analysis my data of this experiment. And at least this is the maximum outer force of my this experiment. And after I do more experiments, I can get data like this. And after I calculate this, I can get a torque and distance relationship. And I use C++ to calculate the R squared, and I get R squared is equal to 0.962. So next part is first part about energy transfer. And what I do in this experiment is I rotate one of them, and I calculate energy transfer between the two visual spinners. So because the energy in the magnet here is rotation energy, so what I need to do is I need to calculate the angular velocity change, and I can calculate the energy transfer rate. So what I need to do first is I need to determine the rotation inertia. So what I do to measure rotation inertia is I use this equipment to measure it, and I use a way to let it have a stable torque outside, and I calculate the time that it passes 2 photoelectric gaps, I can get rotation inertia. And after I put these 4 equations, and I can get rotation inertia, I can express as n times 3 times r squared t squared and divided by 2s. And after I put my experiment data into this, I can get rotation inertia is equal to this. And another way I can measure the rotation inertia is I use a weight, and I use the I equals to mr squared to measure this, and I can get a rotation inertia as this. So after I have 2 ways to measure the rotation inertia, I can get a rotation inertia average is this 0.000536 kilograms times meter squared. So because I have a rotation inertia in hand, I finally can calculate the energy transfer between the visual spinner. And what I do is I calculate the angular velocity change in the motion of, I use tracker to analyze it. And after I calculate this data, I can get average of the energy transfer rate in this condition is 75%. And next part is the final part about speed difference. And first is the maximum speed difference for acceleration, and I try 2 and 3 and 4 visual spinners to determine the number of spinners and the maximum speed difference for acceleration relationship. And first I define what is transmission and what is not transmission. And I define when have a free rolling is no transmission. But if we have a gear merge one torque at a time, I define it as transmission. So I use tracker and Excel to analyze this max speed difference data. And at first, I do an experiment about 2 spinners, and what I do is I calculate the maximum speed difference from the previous driving instance, and at this phase, it happened around 4 seconds. And next thing I do is I do a 3-spinner experiment, and I can get the this phenomenon happens around 1.2 seconds. And what I do measure is I measure the first 2 gears happen the transmission phenomena. And because the 4 spinner setup is likely to 3 spinners, so I still choose the first 2 to determine when the transmission phenomena happen. And at this page, you can see more clearly the max speed difference transmission phenomena happens around 1.2 seconds. So I collect all the data in this chart so I can get a speed difference is almost the same in 2 and 3 and 4 fidget spinner. So I do more experiments, I can get speed difference almost the same. So I think it only have a relationship between the gear itself and the gear beside itself. And I can get a total average is 369 degrees per second. And here's analysis of this. And because when the speed difference is in a certain range, it will generate a driving force and make it rotate. But when it is too fast, it will generate positive force and push it away, so it will happen free rolling. And next one, final part, I want to talk about a maximum speed difference for deceleration. And I use energy to calculate this. And at this stage, the fidget spinner has the smallest magnetic potential energy. And at this part, it has the biggest magnetic potential energy. And after I calculate the magnetic potential energy, I can compare it with my experiment. And my experiment setup is I rotate this one gear and I rotate another gear and I record its motion and use check analysis it. And after I analyze it, I can get a maximum speed for decelerating is around 770 degrees per second. And here's the analysis of these things. And because if the rotation energy is smaller than magnetic potential energy, it will generate a gear effect. So, after I put my experiment data into rotation energy, I can get rotation energy is about this. And I compare it with my magnetic potential energy. I can find it's totally the same, and it is a little bigger than this, so I think this is right. So here's my conclusion part. And first, the gear properties. And in my observation, you can find that gear properties is mainly except two characteristics, the torque and the transmission. And the second conclusion is maximum driving torque. And when I do this experiment, I can get this theory line about the maximum driving torque. So the third part of our conclusion is the energy transfer. And after I do the experiment, I can get an energy transfer rate average is around 75%. So, and at least I measure that when you put more fidget spinner after it, energy transfer rate is around 700%. So the fourth part of the conclusion is the distance, and I tried a different distance for magnetic gear, and I found that the distance between them is negative. Minimum distance is negative 0.25, and the maximum distance is around 4.5 centimeters to 5 centimeters. So I think it's, I take an average is 4.75 centimeters. So next part is final part about speed difference. So, and after I use tracker to analyze it, I can get this data. So I found that the maximum speed difference is only have a relationship between the magnetic gear and the gear beside itself. So that's all my presentation. Thanks for watching.
Okay. Now following the question from the opponent. Please start.
And thanks for your report first. And your theory used in several gears.
Yes, and in my theory, I use the magnetic field to calculate torque, and this can be used as zero and nickel figures.
Okay, thank you. And did your theory consider the damping, the energy loss from the friction or the air resistance?
I calculate the energy transfer like this, and I can get this average about 75%, and this energy loss part is caused by like use friction like that.
Okay. And what do you think the most affect the damping? Which will affect the most? What factors? The air resistance or the friction?
I think the friction, because air resistance is like works more.
Okay. Will the process obey the conservation of angular momentum?
Sorry.
Will the whole process obey the conservation of angular momentum?
And do you mean in my experiment, I do like consider angular momentum?
You obey the law of the conservation of angular momentum. It will, or yes or no?
Do you mean the angular momentum will stand?
Yes.
I think in my experiment I didn't do it, but I think it will stand.
Okay, thank you. And how about the conservation of mechanical energy?
Are they all doing magnetic potential energy?
Since you say that it will have the potential energy and the kinetic energy, and will it obey the conservation of the mechanical energy?
I think if you said the energy transfer, I think is well turn the rotation kinetic energy into a magnetic potential energy, and you will have transfer.
Okay, thank you. And how do you control the angular velocity for your spinners? the initial velocity. You use your hands or you have the motor?
No, but in the energy transfer part, I rotate very fast and I calculate every part.
So you use your hands to rotate?
Yep, time is up.
Okay.
Time is up. Okay, the following time is the preparation of the opponent. Okay, time is almost up, so please start your presentation.
Honorable judges and fellow competitors, I'm the opponent from Team Excel here, and today I'm going to oppose problem number 10, magnetic field. Here's the problem statement. Take several identical fidget spinners and attach neodymium magnets to the ends. If you place them side by side on a pin and rotate one of them, the remaining one starts to rotate only due to the magnetic field. Investigate and explain the phenomenon. So we'll mainly focus on how the passive spinners rotate and rather parameters that will affect the phenomenon and the interaction between magnets of several spinners. And here's the report outline. For the theory part, the report mentioned the attract and repel conditions, and also the stepping phenomenon. And then the report mentioned the magnetic field, how it change will affect the phenomenon, and also the torque, the forces acting on the system, and also the rotation inertia. And then is the magnetic potential energy and the kinetic energy. And for the experiment part, and he has the many parameters, like the magnet shape, and the distance between the spinners, and which is like the boundary for the experiment, and also speed difference. And then he also did how the energy transfer from the kinetic energy from the driving one to the passive one, and also the maximum driving torque, maximum speed difference, and the multiple spinners. However, for the controversy and deviation, he has no theory, error bars and explanation for the deviation, maybe causes from the energy loss, from the eddy current, or the friction. And here are the strong and weak points. For strong points, the report shows clear observation video, and also he explains the phenomenon well and detailed explain how the phenomenon works. And also he has a great calculation of the theory model, and he shows the experimental setup. However, he can't control the initial angular velocity of the spinner stably, and also he explains the chart clearly. However, for the weak points, he has some parameters he did. He failed to consider the radius of the arm. He failed to consider the range of the spinners, since that the problem statement has several spinners. But the opponent thinks that if you have different arrangement for spinners, you will have obviously different results. And he failed to analyze the forces clearly, and he didn't consider the energy loss from eddy current and energy dissipation from the friction. And he failed to consider damping as theory and lack of explanation of different phases of the spinning phenomenon clearly. And for here are the points to discuss. They can be divided into 4 parts. For the first part is the parameter, which can be the characteristic of the magnet and the spinners. For magnets, I would like to discuss how the strength of the magnetic field and the direction of the magnetic force affect the phenomenon, and also the distance between the 2 magnets, how it will affect the boundary limits. And for spinners, I would like to discuss how the rotational inertia, length, width of the teeth, and the angular velocity, initial angular velocity for the spinners possess. And for the theory part, I would like to discuss how the magnetic field and the energy transfer and the torque acting on the system. And for the experiments, I would like to discuss how the interaction between several spinners, which will be the angular velocity, the direction of the rotation, and also the arrangement of the spinners, which can be aligned, cross, triangular, many kinds of arrangements, and also the different turning directions. And for the last part is data analysis. I would like to discuss how the boundary conditions change if you have the different angular velocity, magnetic field strength, and the amount of spinners. And for the last part, I would like to discuss experimental errors, which the report didn't consider the energy loss from the eddy current, and also maybe from the friction and the air resistance. And thank you.
Next page.
Okay, thank you. And can you briefly explain why the other gear spins only due to the magnetic field?
You mean why it only have a outer force about?
Yes. I want to. Can you analyze how the force is acting on the system so that the phenomenon works?
Okay. Wait a minute. Like this part, and you will see. And when because the 2 of the bigger spinners, or you tell it the magnetic gear, is not touch each other, so it only happen on the 2 of the bigger spinners.
I mean that if the spinners are about to rotate and if they are getting close, and how will the repel force be like? It will be increase or decrease, or what phenomenon will be like?
You mean closer?
Yes, if the magnets become closer, as how the forces will act.
Oh, like this. Wait. You can see, and in my experiment, I found that, and the maximum torque, or you say the maximum external force, like this. So caused by the magnetic field, and the maximum range is when the 2 bigger spinners is tension.
I mean how the force is acting. You just short answer. If the repel force will become bigger or smaller?
No,
if the magnets are getting closer.
Yes, I think just this. When it's closer to 0 centimeters, and the magnetic force were bigger. When you put a magnetic field too close than wait. Here, this situation will have the maximum repulse force, and when you when you put a gear more closer here, you will have a more bigger force than this situation.
Okay, thank you. And can I use the whiteboard? Thank you. And can you show me how the energy transfer during the whole process, which the charge need to include the kinetic energy, the magnetic potential energy, and the whole energy. And then this is the initial kinetic energy, and what will it be like if this is the kinetic energy?
and magnetic potential energy. Can you draw me the chart?
Let me turn the PowerPoint first.
No, I only want you to draw me the chart.
Yes, but in English you see it clearly. And in this part you will see the
and this is the angular velocity. I'm wondering how the energy change, not the angular velocity.
And because the rotation energy can be expressed as this, right?
Yes.
So I have this, I can call it that. So, and because in this direction you will find omega 1 to a 0, so rotation kinetic energy, and you will have a cycle, and so you will like this. And whenever you have this,
so it will gradually decrease, right?
Yes.
And what about the?
In the decrease at this side, and energy will transfer into the magnetic potential energy, and at this part you will translate energy back to the kinetic potential energy.
So can you draw me the line for the magnetic potential energy?
It's usually like at this part. So this is.
You can draw the total energy first. The total energy.
Total energy in my experience was like this.
Can you explain why it will decrease for this line?
Because in real life you will have some it won't just have the
it will have energy loss, right?
Yeah.
And what may cause the energy loss? What affect the most? What factors will affect the energy loss? Okay.
And I think here is about the friction of in these two.
Only the friction, no air resistance. What should affect the most? Air resistance or the friction?
And I think it's friction because I don't know why you talk about air resistance in this part.
This is a spinner, right?
Yes.
And it will have air resistance. So it will cause the energy loss, right?
But the effect is very small.
So you think that the energy loss will only affected by the friction?
At least even more.
And what about the eddy currents, which will generated on the magnets?
How about you say eddy current? Can you explain more about your version?
So I mean that the eddy currents. Do you consider eddy currents in your theory or your experiment?
And usually I don't consider it. Eddy current, and when you have a bigger magnetic potential energy, I think it will have equals to have if you think these are have a shape, and it will have more.
Okay, thank you. And well, the initial position for the gears, if this is unfold. And well, the initial position, right? You have given angular velocity, right? But before you give an angular velocity, well, their their position for the spinners affect the result. If maybe like this, or which degree?
Oh.
Well, it affects.
And in my
is the yes or no? It will affect.
What do you mean?
If you place the gears in different directions, the different initial place, and well, it affects the result. Yes or no?
Let me talk about. And when you happen to transfer phenomena, it don't have the. It's not important what angle is initial condition.
So you mean it is not important?
No, I say when it happen to transmission phenomena. Here, I mean when it happens, the transmission phenomena, first,
their distance are different. I mean, in the same distance.
Yes. So
and you change the degree, and will it affect the phenomenon? Yes or no?
The difference,
I mean, okay. If they are in the same distance.
Yes.
Like this, if this is maybe 3 centimeters, and this one is also 3 centimeters, but the angle weight is different.
Yes.
And will it affect the phenomenon?
It will, if you the initial distance like this, and the initial angle will affect what the initial rotation speed you can provide it. But if the rotation speed is more, then it's okay. It's not important.
What do you mean it's okay?
And I mean when this can happen, the measure is mean the rotation speed is okay. Not the speed difference is not too rough. Like my experience, I have said max speed difference, right? And here I define what is transmission. So I think if you have a transmission, it will.
Okay, and how can you optimize the convert efficiency? The energy convert efficiency. Do you know what I mean? Optimize the energy. So that maybe you rotate this one first, and this one will rotate due to the repel force, right?
Yes.
And how can you that this one the energy will convert to here, right? And how can you that the convert efficiency be the best?
In my experience, because the repel force is caused by magnetic force, so and in my experience, I have told you that the maximum magnetic force is happened by the two figure spinner tangent to each other. So I think that when the distance is tangent to each other, is like tangent to each other, it will have the best.
So will other factors besides the distance, will other factors can optimize the converge efficiency? Maybe the T, the amount of the T, maybe five, number of 5 with T. Do you know what I mean? If you have 5 T's, and well, it converts the energy well, better.
At least if the magnetic force in here is more stable than this, I think maybe well, but because it's not in my experience, I predict it maybe well. And you need to consider about the arm of this.
Okay. And what about the moment of inertia affect the phenomenon? How will it affect the moment of inertia?
So moment of inertia is affect this.
I mean, how will it affect the transiting efficiency, the energy transiting efficiency?
In this part, I think it won't be the most important part of this because
I mean how?
Okay. Time is up. So following opponent, please give your 1-minute summary about discussion.
And here is the discussion summary. And for the first one, I discussed will the initial position affect the energy transfer condition. However, the report thinks that it won't affect that much, but the opponent thinks that it will affect the energy transfer condition. And then the second one is kinetic energy of the driving side will transfer into the magnetic potential energy, and then will transfer into kinetic energy for the passive one. And this is the explanation of the whole process. And then is the cause of the phenomenon. For the energy is that kinetic energy will transfer to another gear's kinetic energy. And of course, when the magnets get closer, the repel force will become bigger. And the friction and resistance energy loss from the eddy current will cause the energy dissipation. However, the report only thinks that the friction will affect the energy loss the most. And the opponent thinks that the method to optimize the converter efficiency is to increase the number of teeth, increase the moment of inertia of the driving spinner, and also the distance. Thank you.
Okay, so reporter, please stand up. Opponent, please also stand up and please be ready to answer the question from the reviewer. Yeah, please.
Right, so first question I want to ask the reporter. So you draw the total energy line, right? So why would it be linear when you draw it?
When I draw it here, it means I think the energy will loss, but I don't know if it's linear or not because you can calculate the energy loss at here. You can calculate it.
Right. So what do the other think?
I think it will. I think the damping will be like exponential damping.
All right, exponential. All right.
Yes.
So got it. So you mentioned damping, right? So can you explain how would it affect in this phenomenon?
And if there are no damping, the spinners can rotate continuously forever. And so the damping from maybe the friction, air resistance, and energy loss from the currents will cause the damping, and which will gradually decelerate the.
Okay. So what do you think would affect more? So air resistance, friction, or whatever?
I think the friction will affect the most.
So what does the amount mean?
You mean the most affect is energy of most?
Yeah.
I think is the friction of the unit.
All right. So please turn to page 92. Here. So this is quite confusing. So can you please just explain it more about, shortly, briefly explain it. So what does it mean?
This means the magnetic field and one magnet doing the magnetic field to a point. Yes, means to this point is to the magnetic field.
All right, got it. So so for the reporter more. So can you how do you define the freewheeling? So can you explain more? How do you define the freewheeling?
At my video, actually, like this. If you have
can you turn to the video where you have the video of freewheeling?
Okay, wait. Like the first part. Like here. Wait. This.
Right, but do you measure that? Do you think that the small oscillation is caused by the magnetic force?
Yes, this is caused by magnetic force. I have a.
But don't you think that freewheeling it means that the blue one wouldn't be affected by the yellow one?
Oh no, but this is my finding in my experience.
All right. Okay. So how do you measure the potential energy?
Magnetic potential energy.
Yeah, magnetic energy.
And I calculate the magnetic field, and I use the equation to calculate.
All right. So how does he calculate?
Maybe you can use the equation that he has for the equation formula for it. So you can calculate it.
All right, got it. Thank you.
Okay, now is the time for reviewers' preparation. Time is up. Please start your presentation.
Alright, so I'm the reviewer from Team Excalibur, and today I'm going to review problem number 10, which is magnetic here. And so the problem statement is that take several identical fidget spinner and place it side by side, and rotate only one due to the magnetic field. And so you need to investigate and explain the phenomenon. And so they use magnetic field explanation and torque analysis and angular momentum and attraction and repulsion, which they use different distance to analyze. And the magnetic potential energy and boundary condition to explain the theory. And the experiment part, they use different parameter, which is distance between fidgets and the number of spinners and the weight of magnet, which would affect the rotational inertia. In the setup, they use force sensor to detect the force, and the analysis they uses energy transfer and magnetic spinning speed and magnetic driving torque and transmission to analyze it. And so the results are when the distance increases, the maximum driving torque also increases, and the average energy transfer rate would be 0.75, and the speed of the driving spinner would affect the energy transfer. So about the reporter, I think he had a good qualitative phenomenon explanation and small physics explanation, and they did various parameters, and they give specific data for the experimental setup. And so for the suggestions, I think they lack of explanation for the derivation process, and the method to analyze the magnetic field is quite weird, and they need to consider about the different position of fidgets, and they lack of explanation for the measurement setup. Also, so this is summary for the opponent. So they asked about the maximum speed for the accelerating and the damping effect, and also the air resistance and friction effect, and the conversion of kinetic energy. So the experiment part, they asked about how to drive the spinner by using the hand or by using the other machine, and they also asked how to control the rotational speed. And for the strength problem, I think he asked about some missed points such as friction, measurements, and he focused on specific process of energy transfer, which I think is very great. And I think he can consider about the magnetic placement more, and I think he should provide the opinion about the search in the report. All right, so first, the opponent asked how does the force act on the spinner. So the reporter answered that when it's closer to 0 centimeters, the force would be bigger. And I think that he should show more clear graph about the force interaction, which they did draw, but I think they should show it in the report. So the opponent also asked how the eddy current act in this phenomenon. And the reporter said that they didn't detailedly analyze it. And I think that they also should clarify the definition of eddy current in the system before they discussing it. Yeah. So, all right. So the opponent also asked how the initial placement of the fidget would affect, and the reporter answered that it would affect the repulsion force between the magnets. And I think that the reporter should explain the interaction of the force more clearly, as I said before. And also, so now when I asked why the time and total energy is linear, and so the reporter said that they just draw the line, but they didn't know if it's linear or exponential or something. And the opponent said that I think it's exponential, and I think that it will not be linear, but if it's exponential, I'm not quite sure. And I also asked how to measure the potential energy, and the reporter said that they use magnetic field to get the magnetic potential energy, and the opponent said that they should use the equation. And I think that the reporter should mention more about how to measure the magnetic field. Yeah. Thank you.
Okay, so following is the time for concluding remark from the reporter. Please start.
Hello, I'm this reporter, and here's my concluding remark. The first is a power statement. The power statement is you take 0 spinner on and place them on a plane, and you rotate one of them, others will rotate only to the magnetic field. And here's my report, and I try and repulsion to find a stable way in the arrangement of a magnet, and I use the magnet to do a torque analysis, and in my experience data, and I found the energy transfer in my situation is 75%, and negative I do a rotation energy, and I use the rotation inertia to measure the rotation energy. And in my setup, I use several identical sphere spinners, and I use a magnet, and I use a motor to let it spin continuity, and I use a force sensor to measure the external force that was provided by the magnetic field. And here's a parameter. I do a different distance and track of reports, and I do a different for the different spin, and I have to do a lot of spinners. And the discussion and for the analysis of force in the model, I think because we do not touch each other, so it only have a magnetic field repulsion. And finally, with the spin get closer, it does something concurrent, and you have a phasor conversion, but the phasor, the effect is when it's tangent to each other, so it's 0 centimeters. And they asked me what affects the energy conversation most. And I think it's a friction. And the opponent says I have a damping. But I don't know why you have a damping part in this my phenomena. Yeah, the next one, well, the initial position here is very so I think well, it will affect the maximum rotation speed different, but it is rotating well, it's not affect anymore. And what happens with the multi-sphere, I think it will be more stable. And then how to calculate the magnetic potential energy. I use the equation in my report so I can calculate the magnetic field here. That's all.
Okay, thank you. So I would like all three presenters to be on the stage and be ready to answer the question from the jurors. So, yeah, please.
Okay, for the opponent, in your discussion point, you mentioned about the critical velocity, angular velocity. What do you mean by critical angular velocity?
What do you mean? I said
in your discussion point, you mentioned about the critical angular velocity.
Oh, I mean that maybe it's angular velocity. And can I use the whiteboard? Okay. And if we have two spinners, and we will rotate one of them, and if we rotate this one, and due to the repel force, so this one will rotate. And I'm wondering if the angular velocity of the initial angular velocity of this one is very small. Will this rotate as well? And if the angular velocity of this one is very high, will it rotate as well? I want to discuss this.
Okay, thank you. For the reporter, do you think you can answer the question, or you already done the experiment?
Yes, and I think I can answer this question. And in my report, I have said that it has a maximum speed difference for transmission. And so when the speed is rotation speed is very small, I think it will affect the transmission part. But when it's too fast, like I say in my experiment, it will have the free wall phenomenon.
Okay, so do you find the critical angular velocity?
Yes, and the maximum in my experiment is around 369 degrees per second. Yes, I have find it here. This is the maximum speed difference for acceleration.
Okay. Any further questions? Yeah, please.
I'm discussing the dissipation, and most of you agree that the most important effect will be from friction. Do you have any experimental data or argument to support this conclusion?
No, I didn't agree with it, but I also didn't know about that.
Do you have in mind what argument or what experimental data you can show us to support your opinion?
Maybe I think they can do more experiment about the force they interact, and maybe we can know about that.
And I think that maybe they can try to measure how the friction, how big it is, or how the air resistance affects, and compare with it, and you can find the results.
No, and in my opinion, and I think even though the friction is not in my experience data, but I think the friction will affect another than air resistance, because in my here the area is very small, so I think the air resistance will affect it more. But in the friction will likely decrease the well, it have the energy loss, and it's because and my setup is the most that you can see is friction.
Okay. Any further question, please?
The reporter, you show a graph of maximum torque versus distance on page 28, perhaps. Is that, yeah, and you have a solid line. Is that a fitting from the experiment, or it's a prediction of your model? The solid line.
This line.
The solid line?
Oh yes, this line is in my theory line, because
where is your prediction?
Here. Do this.
Do you have a
Question?
Yeah, equation.
Because I have a measure list magnetic field, so I sum them up and sum one and
I think it is no simple form, right?
Yes.
Okay. Thank
So
you.
sorry for some time.
Okay, thank you.
Any? Yep, please.
Okay. This theory is statement is just typical magnetic field theory. Now, there are two important quantities to start the magnetization or magnetic moment, and also the field generated by these dipoles, right?
Can you explain your question more?
Your theory actually starts with some magnetic moment and magnetic field generated by the others, like force torque, they just fall, right?
And if you mean I calculate.
Do you understand that all your theory is just based on these simple things? Right? You have a dipole moments, right? Negative is characterized by dipole moment. Are you aware of that?
Oh yeah,
But you didn't measure.
Did you measure the magnetic field around your magnet?
Yes,
single dipole line.
single point.
Assume all the dipoles are the same, of course, right?
Yes.
You should actually first investigate how accurate your formulas are correct.
But when I understand and because I was strong enough, I think I can calculate that.
There's major. My point is that the theory is dipole moment. You use the dipole, the magnetic dipole moment, right?
And so a fast dipole moment.
You only calculate the magnetic field, but did you measure it?
In the experiment,
Make sure that the formula works with the precision you want.
Because I use this and I calculate torque, and the torque and with my experiment is very matched, so I think this can be.
So you only measure the torque?
Because it's used by.
Yeah, you only measure the torque, right?
Yes, because
I think that's the answer Professor wants. Okay, because the time is already over. Yeah, so. Okay, so we proceed on to the scoring part. Okay, since all the scores were given, so we start from the reporter's score. The scores are, okay, 7, 7, 7, 7, 7, 6, 5, 4, 7, 8, and 7. And the scores for the opponents. They are 8, 6, 8, 7, 8, 7, 7, 5, 7, 7, 8. And scores for the reviewer. Seven, 8, 6, 7, 5, 6, 8, and 8. Okay, for the reporter, we got a very pretty high mark, about 8, and plenty of 7, and 5, 6, 5, 4. For each has 1. So any comments about the high score?
The reporter gave the presentation in a very well organized, with a very organized logical flow. He showed that he found the limits of the experiments first, and then he found the parameters first, and then he conducted the experiments within the range, and then presented in a nice way. I think that's the reason I gave a better score in the presentation.
Okay, thank you. And there are some low scores. So any comments from the low scores? Yeah, please.
I'm consistently low.
Okay. Oh yeah, that's okay.
But the main point is, it seems that the reporter didn't actually bring out the essence of the problem. So as a gear, what is meant by a gear? So of course the important point is the torque and also the energy transfer. It has, but it's not well presented. The experimental method, I don't think it actually does do the job.
Okay. Yeah, I heartily agree. I think that for the measurement part, something like the torque, this is something that you better directly measure it, or you measure the force and convert it to torque. But seems here your torque not clearly say how you measure it. Yeah. So any comments?
About the reporter, you did the presentation well, but during the discussion, I think you didn't respond well to the opponent.
Yeah. Okay. And for the opponent, we got several 8, several 7, 1, 6, and 1, 5. So for the high scores, any comments? No comments from the high score. So any comments about the low score, the 5 and 6? Yeah. Okay.
I will go first. I think the opponent will spend too much time arguing speculated question like is friction or eddy currents or whatever. The report clearly didn't include these parts. So all your questions are just theoretical asking answers, and that's not what the opponent is.
Okay.
Just a short comment to your opponent. At the beginning, I'd like to give you a high score, but after the first part, in your discussion point, you give a very consistent list. But I don't think you follow the points very well. You give too many open questions. You give an open question, then the role will be played by the reporter. Yeah, you cannot control. You don't control it very well, following your points. Yeah.
Yes, I think I can add some comment. If you are asking something like the friction, and it doesn't show that very clearly, so if you want to emphasize that part, better you can extract the friction from his data or provide a method that you can show it can be extracted. Okay. Otherwise, I don't think it's a good point to emphasize. Okay, and then we go to the reviewer. We have 1526, several 7, and several 8. So any comments from the high points, from the 8 or 7? Any comments about the reviewer? Yeah, please.
I think reviewer did a good job and present very well. Just control the time, and even though his brain wants to show the time limit, but he can control by himself very well.
Okay. So any comments from the low mark about the 5 and 6?
It's already good for me.
Okay, I understand that. I think it's quite even. Yeah, I think one thing important for you is that all of you mentioned about the potential energy, but seems no one calculated or show how to measure it. So I think that for opponent and the reviewer, if you mention that, better not only mention by name, because it's something like empty words, because you cannot demonstrate to people that you really know how it was extracted. Okay, so I think that's one important physical idea. Okay.
Actually, potential energy is not very good term. It should be interaction and
because in this question, actually, if you mention about the magnetic field, the potential energy is not a scalar. Okay, but for the gear, maybe you can express somehow, some way, that potential like energy, but you need to introduce that to people. Otherwise, people are not easy to understand what you are talking about.
I'd like to suggest to the reporter that if you have magnetic interaction, you can calculate the form as well as the form. Just by partial differentiation with respect to displacement and angular displacement.
Yeah.
I don't think you realize that.
Yeah, I think
they
will know.
This important relationship between interaction energy with the form and form. It's simple form.
Okay, I think we are already reached to the end of this third round of the final physics 5. So I would like to close the section here and announce that the final physics 5 already ends. And let's go to the dinner room to have lunch. And we will come back here around to have the closing ceremony in the afternoon. Okay.
这个校好像在啊，英校台湾留下来吗？
应该不会吧？要留下来，你要用哦。
我好像在必须来录闭录，要录闭录吗？
你要用的话，我就留下来给你。
问题有没有人操作啊？
没有。
校这边应该满坑满谷的人。我看莫妮刚会不会留下来？我看。
他们可能会，但是。